So let me introduce Stéphane Louboutin. Okay, we're very happy to have him talk about the application of Stechkin, Stechkin's lemma to lower bounds for L1 chi and single zeros of Dedekin's Z function. Please.
Okay, so thank you to the organizers for this invitation. So I will only speak on half of the lecture, or half of the topics given the title. I will only speak about the real zeros of Stechkin's Z function. So the notation is pretty standard. So K will be a number field, dk is the absolute value of the discriminant, zeta k of S is the Stechkin's Z function, hk is the class number. So the notations are pretty standard. So when we look at the real zeros of zeta function of number fields, if let me just give you a reciprocation. We take k, small k, imaginary. Okay, I assume that this k is not neither this one nor this one. This fields are class number 1, I don't care about it. So in that case, the class number formula is that the class number of k is just the square root of the absolute value of the discriminant of k divided by pi times the residue at s equal 1 of the zeta function of k. Okay. So one simple way to get lower bounds on class number is that you have a very general result, which is so when I wrote small k, it means a quadratic field, and when I write capital K, it means any number field. Okay. So you have a very general result, which is something like that. If you know the sign of zeta k of S very close to 1, or some beta between 0 and 1, then you have a lower bound residue. Okay, so first of all, you must notice something that if you look at the representation of the zeta function of a number field, it's you have a pole here. So if you use a series, the Dirichlet series of zeta k of S, it's very easy to see that in this part it is decreasing towards 1. And at S equal 1, you have a simple pole with positive residue. So what you know is that here you come from minus infinity. Or at least you know that the zeta function of k is less than 0 when beta is very close to 1. Okay? But of course, you want beta to be not close to 1, because the closer beta is to 1, the smaller this part, and when you plug this one into this one, you end with nothing. Okay, so the key point is that if you look at that, this is optimal. So you want that to be as big as possible, and this one is optimal for beta equal 1 minus 2 over dk. In that case, you end up with okay, so what does this mean? It means that if you know that there is no zero, so you have the graph here. If there is no zero, then it's negative. So if you know that there are no real zeros close to 1, and if you can reach this point, then you have a very nice lower bound on the residue. And if you plug this one into this one, you end up with that the class number is very large. Okay, so here we have a definition. So I will be always looking at the zeros in this range. So what we call a Sieg zero. So you choose the C here. So it's equal 0. Sorry. Which is in some range or something like that. So you don't care exactly what the value of C. So I don't know if I put it in a bit more. Okay, so what I explained here is that if you have no Siegel zeros, then you have a very nice lower bound of the class number. So of course, nobody knows how to prove that there are no Siegel zeros, so this is not a main topic. So what can we say about Siegel zeros? So it's a very old result of Stark. So it must maybe taste like earlier than that, but it's in the famous paper of Stark on the effective versions of the Siegel theorem. At this, so when I say when I count zeros, I count them according to their multiplicities. Okay. So the result of Stark is that if you take C equal 1/4, in that case, the stacker of S has almost one Siegel zero. What I mean to say is that in the range 1 minus 1/4 log dk1, there is at most 1 0. At most, yes. At most, sorry. So of course it doesn't tell you that it doesn't have any Siegel zero. Okay? So at least you can say something using this result. You can have the corollary. You can easily show that fields with Siegel zeros are few and far between. So for example, let me just show you that the corollary of this result is that given x large, the number of quadratic fields that can have a Siegel pattern zero. So here I take C equal whatever 24, I think. So there is no. So the definition of the Siegel zero depends on your choice of C. You don't care that much of the choice of C because of the lower bound I gave you. The lower bound is the square root of dk over log dk times C, roughly speaking. So you don't care about the size of C. Yes.
Say maybe arbitrary large, or is it supposed to be?
No, usually, what I told you is that you would like to use that with C equal 2, because this is the optimal choice. So usually C is not very large. For example, in Stark's result is 1/4, and we would like to have a result with C equal 2. So in fact, this is the main topic of the lecture. I will explain you how I can get a much larger range. So just to give you something, so for example, the number of quadratic fields which have a Siegel zero, where for the definition of the Siegel zero I use the constant 1/24, is very small. So of course the number of quadratic fields of discriminant S, sorry. Less than x. So the number of fields is linear in x. And so this means that it's very unlikely to have a Siegel zero, at least for a quadratic number field. So the proof is very easy. It's a really a corollary of this one, because the idea is that assume that you have two quadratic fields which have Siegel zero. So of course you may assume that the discriminant of K1 is less than the discriminant of K2. Okay? So the idea is that you build the fields for which you have double zero, and you will know that this is not possible according to Stark unless. So let me just write on the proof, it's very easy. So what you look at, you look at the quartic field, which is the compositum of the two. So you have the diagram, something like that here. You have the rational number fields, you have your two quadratic fields. And K is a quartic field, which is a compositum of the two So of course there is a third quadratic subfield here, which I call K3. Okay? So it's well known that in this situation you have a factorization of the zeta function of K, that the zeta K of S is just the product of the three. So I will always use the real variables. S is the real form. Divided by the square of so zeta of the number field Q. So of course this is the given zeta function. Okay, so if you have a Siegel 0 for this one, and you get 2 zeros for this one, of course this one is positive on 0, 1. So you get 2 zeros for this one, so it means that so this one has 2 zeros. So be careful because the range is not the same for the two zeta functions. The definition of the Siegel 0 is the range depends on K. Okay. So this one has a real 0 in this range with dk1, this one in this range with dk2, and since I assume that the largest range is inner. Okay. So using Stark's result to deduce that this bound must be less than dk. Okay, because you have at least 2 zeros, so you must be to the left of this range. Okay, and so you convert that, this is equivalent to asking that dk is greater than dk1. So it's a 6, okay? And now it's very easy to see that you have a formula. You can use the product here to get the formula. You use the functional equation and you deduce that the discriminant of k is the product of the three. So I will write it here because it's some calculation. So dk is just the product of the three. And of course, the discriminant for a quadratic field is the same as the conductor. And of course, the conductor of 3 divides the product of the two. So this one you should divide dk1, dk2, square. Okay, so it means that dk is less than dk1 square, dk2 square. So I made a mistake somewhere. Yeah, it's okay. So the two of them implies that dk2 is greater than dk1 squared. Okay, so what did I prove? I proved that if I have two quadratic fields which have a Siegel 0, and if the discriminant of the first one is less than or equal to the discriminant of the second one, and this one is much bigger than this one. And if you put everything together, you end up with this one. Why? Because if you assume that you have many fields which have a Siegel 0, you can sort them according to their discriminant. Okay, and if you so the discriminant to this one is at least the square of this one and so on. So it's very easy to see that dk1, dkn is at least dk1 to the 2 to the n minus. Maybe 1 here, I don't care. And of course the discriminant of k1 you don't know, but the smallest discriminant is 3. So it means that n is less than constant times. So this one is less than x. So if you have n fields which have 0, 0, then n cannot be too large. What I said. Okay, so we don't know how to prove that even quadratic fields don't have Siegel 0, but at least the quadratic fields which have a Siegel 0 are few and far between. Okay? Okay, So I will explain you later on why it is very interesting to have something. The problem is that here is dealing only with simple zeros. So I will give you a statement which deals with simple zeros, and then I will explain you why it is much useful, more useful than this one. So I will give you an idea of the proof of sparse result by giving you a proof of a more general result. So you give M, then Stechkin almost at most M zeros in the range of sigma M1 and sigma M is close to 1. So it's like for the 0, I have a range with something like that, where and Cn is just 2 times square root of n plus 1. Be careful here. So n plus 1 minus 1 to the square. Provided that decay is large enough. So it's very explicit and it's not very big. I don't remember. I will write something. I think it's something like that. It must be 2 times n plus 1. Maybe it's something like that. What I need to say is that the n is fully explicit and it's not very large. So usually you don't care about that. That's why I put this condition in parentheses. Okay, so let me recall that when I say at most n zeros, for example, it could be a single zero of multiplicity n. Okay, I count them with their multiplicities. Okay, so if you look at, I told you that what I want to use 0, 0 with equal to. It means I want to use this. It's very easy to see that C3 is equal to 2. And the result of star is for n equal 1. And for n equal 1, here you get something slightly better than star, because for n equal 1, here you have something which is close to 1/3, not 1/4. But you don't get that much anyway. Okay, so I'm sorry that I have to give you the proof of that. It's quite short, it's not that just because the main point of the lecture is to give you an improvement on this result, and if you want to see where does the improvement come from, you have to see all the detail of the proof. So it's not that very difficult, okay? Okay, I always forget what are the exponents. So the key point is that you start from the psi function, which is the one which satisfies the functional equation and which is built from k of s. And you want it to have no poles, so you kill the poles, and you take this one, so you have a decay. That's where I use this one. Okay, so here pair 1 is I told you the notation is pretty standard. This is a number of real embeddings of k. This is the degree of k. This is a discriminant. This is the gamma factor, which appears in the functional expression. So you have a pole here, and due to that s equal 1, and I want to kill the pole, so I put this factor, and I want to keep the functional equation, so I have this one. Okay? So what we know is that this one is entire order 1. With a functional equation. And moreover, you have a 0 and only if its conjugate is also a 0. So it means that I can pair them up. A 0 coupled with this conjugate. Okay? So if you have an entire function of order 1, so it has some infinite product, a very simple one, and you take the derivative and you end up with something which is very clear. You get when you take the sum of all the row, you always mean a 0 of the zeta function. So this is the logarithmic derivative of this one. So this one is the logarithmic derivative of this one, but I move it to the other side. So this one is and this is you can use the Dirichlet series expansion, at least for s greater than 1. And the point that is very easy to see that all these coefficients are positive, are not negative. Okay? So you don't care that much because the point is that this is positive. Okay? So this is the derivative of the left-hand side together with this one, and now I take the logarithmic derivative of this one, but you don't care because the main point is that you take the logarithmic derivative of this one, you get this one. You take the logarithmic derivative of this one, you get this one. And then, I don't care, you just believe me and you just have to check that. You put everything else in this factor. So I mean the logarithmic derivative of this one, this one, this one, and this one. Okay? And you have something which depends on R1, and it depends on many things. At least of, sorry, here you have R2. So it depends on R1, R2. N is just this one plus 2 times this one, so I don't care, and of s. And roughly speaking, this is a linear combination of the logarithmic derivative of the Gala function. Okay, so the point is that you don't care that much because I just want to have an inequality, so this one is positive, so the left-hand side is at least this one, and I want to have an upper bound on this one. And the point is that it's very easy to see that this one is negative. So I don't remember the value that you don't care that much. I think it's up to 2, no? I don't remember, but so you don't care, it's an explicit value. Maybe 2 is okay. I think 2 is okay. Okay, so the point is that I don't care about this one, it is positive, and I will say that this one is less than this one. Okay? And the point here is that if you look at these factors are, you can write them this way. Okay, and of course all the zeros of the zeta, they satisfy that they are in the critical, they are in this range. Okay, so it means that all these terms are positive. Okay, so what do I do? Is that I just want to have an upper bound, so the point is that assume that you have a test. In the range, in this range. So what do you forget about everything except for all the zeros you have here. For these zeros, it's very to see, so they are real, so you don't care about the real part. And this one is greater than, so you have to take the smallest one. Okay? So you get that the left-hand side is at least n plus 1 over minus that, and it must be less than the right-hand side, and you forget about this one. And I move this one to the other side. It's less than. So of course this is valid only for. This is because of these conditions that I have something like that here. And now you get a contradiction. It's very easy because what you take is you look at this function of sigma and you take the value of sigma for which it is the largest possible. for which the value of that is as large as possible. So it's very easy to see that the optimal choice is square root of I think this is the So you take for sigma this value, which is the value of sigma for which this is as large as possible, you plug that into that, and you end up with a contradiction because for this value, the left-hand side is equal to that. So you can see the proof is not that complicated. Huh? Okay. So I told you I want to explain to you why it is much better to have a result where we can deal with multiple zeros. So there is a second result of starting the same paper, which is a very nice one. It tells you where do the bigger zero come from. So you have to assume that K is Galois. And you take any real simple zero. I wish I could read that actually. You take in this range, of course, a simple real zero for the zeta function of your number of your Galois number field. So the result of start is that then there exists a quadratic subfield I told you a small k means a quadratic. It's a very nice result. It tells you that a simple zero comes from a zero of a quadratic subfield. And I explained to you that the fields which are the quadratic field which are the legal zero are very few and far between. So this is okay, so the key point here, you deal with simple zeros. So I don't want to explain the proof here because this is using Hartin's formalism, using Hartin's L series and things like that. But just give you a rough idea of the proof. Let me prove that in the case where case of Q is abelian. Just to show you where the L series are used. Okay, so in that case where K is abelian, of course you know that you can factorize the zeta function of K. Just take all the characters associated with K, so K range over some subfield here, which I call it. So this means derivative characters. Okay, so the point is that, here I mean primitive derivative characters. So the point here is that if you take the trivial characters and you get the zeta function, and you take the quadratic ones, but not trivial ones, and you take the other ones. Okay, so this one you know that this one is less than 0. It has no real zeros, this one, in this range. And this one, is, the point here is that this one, the non-quadratic characters, they come in pairs. Okay, so you can group them in pairs, and if you look at that, this is just the square twice real. Usually this one is just this one. So if this is real, I don't care, okay? Square of the body of the same. Okay, Okay, but the point is that if you have a 0 here for this one, it must. So all of them are holomorphic, and that's why the proof for this case is much more difficult because we don't know if Artinel series are holomorphic. Okay?
Large K is imaginary.
No. No, it could be a real.
Okay.
So all of them are holomorphic, so if you have a 0 for this one, it must come from a 0 of these ones. But if one of them here has a 0, then this one would have a 0 and you would have a double 0. And it's not, and you are dealing with simple 0. So if you look at that, it means that it comes from one of these L functions, and these L functions are L function associated with quadratic characters. So these are L function associated with quadratic number fields. So the proof of this result is very easy for the abelian case, but the point is that you are using to factorize the zeta function using L functions. And to prove that, you do the same thing but using Artinel functions. You have to be a lot more clever. They are not holomorphic. Yeah.
So there is this L function that Armitage found that has a real 0. Does that mean that it's not Galois that pure works really? Or am I completely mistaken?
No, it says that they are not simple zeros. And so you mean they vanish at s equal 1/2?
Yeah.
Yeah, they are not simple zeros. Yeah, they come from dihedral number fields.
Okay.
They have even multiplicity. No, there is no comparison. Yeah. Okay, so what is the use of this result? Just let me show you a very simple application of this result is that you take a Galois number field of all degree, and in that case, this one is less than 0. And this is exactly what I need to get Lava bound from the residue, okay? Using stars. Why? Because in this range, according to Stark theorem which I erased, you have at most one simple 0. And this simple 0 from this one must come from a real quadratic subfield. But you took something of odd degree, so it does not have any quadratic subfield. Okay, so using Stark's result, you get that. And what is the use of this one? So I don't know which three. Using theorem 3, you have something that's better than that. You have and C2 is just 2 square root of 3 minus 1 square. I don't know exactly the value, but if somebody has a computer, it's greater than 1, I don't remember exactly. So it means that this one is 4 times to the left of this one. So I just want to show you why this is true. And this is the main use of using multiple zeros. You just have to look at the graph of zeta k. So I told you here, so of course I'm looking at the graph to the left of the vertical line. Okay, so I told you that we have a simple goal of positive residue, so I come from minus infinity here, okay? Okay, I want to prove that I am less than 0 at this point, okay? So what is the problem is that first we can have zeros of even multiplicity. So I have my point here, which is 1 minus C2, and I have the decay. And I want to prove that zeta k is negative on all this range. So to the contrary, I assume that it is positive here, okay? And I will give you a contradiction. So if you have an even multiplicity, you don't change the sign. So what does it mean? If you want to end up at this point, you have to cross the line sometime. So you have odd multiplicity here. So if that not were true, I would have a 0 of odd multiplicity in this range. But of course, the the argument is the same, the degree is odd, so there are no quadratic subfields. So it means that this one is not simple. Because if it were a simple 0, it would come from a quadratic subfield. So it means that the multiplicity is at least 3, and in this range, it's written here, with C2, you have at most two zeros. Okay, I just give you a sketch of the proof, just to show you how useful it is to have something with multiple zeros. The statement with multiple zeros. Okay, so here I told you this one is much better than this one, but I told you that I wanted to end up with this one. I would be glad if I had something like that. For example, I would like to prove that there is at most 1 0 0 in this range. I don't know how to prove that, but what I want to do is I want to have the same result here, but with something bigger than this one. Okay, and so this is the new result I want to explain to you, and this proof uses Stechkin Lemma. I have the same result, but with a slightly larger range. So the definition of I will put it here. Okay, so the C prime n is just 5 square root of 4 times the previous one. So this one is greater than 1, so this one is larger than the previous one. So I can widen slightly the range in which my results are still true. Okay? And if you use the same proof, of course, you end up with the same result, but instead here you put C prime 2. And if you look at what is C prime 2, I don't know, you just have this one times this factor, and this you get almost what you wanted from the beginning, because this one is almost 2, but not 2. Okay, so I wish I had obtained 2, but it's only one. Okay, so the new result is this one, is that we can widen the range in which we can control the number of real zeros. Okay? So I'll give you the proof of the previous result, because the proof of this one is a little bit more complicated than the previous one, but it starts, the starting point is almost the same. So here again, you start from exactly psi of k, the same as I used. So you have the gamma factors and things like the same. Okay? Okay, and here again I use the infinite product, so it is an entire function of order 1 with a functional equation. So here I will use, in the previous proof, I use the pairs rho bar. Here I will group the zeros in pairs rho minus rho. So here the point is that if rho is a 0, if and only 1 minus rho is a 0. This is due to the functional equation. Okay? And you do the same things that I did, so you take the logarithmic derivative and so on, and you end up with the same. So it's almost the starting point is the same. So you end up with so sigma will be real. So for S I don't care. So let me recall that this is just this one. And let me recall that this one was a Dirichlet series with non-negative coefficients. Okay, here I take the sum of all the zeros. And as I did before, I have the 1 minus 1. But here I have to be a little more careful. I keep this one. something else, which I take the same notation, but it's not exactly the same one as before. And I drop the error there too, because in the previous proof I have increased this one with this one. Okay, the point is this. And I will use this expression to prove theorem 4. So remember that the key point is that we assume that we have at least m plus 1, 0, and we ended up with something like that, which was this is the end of the I had something like that, and then I choose sigma to get a contradiction. Okay? And the point here is that to get a larger range here, I want to have something smaller than 1/2. The smaller the coefficient here, the better the result. So the question is how small can I take the coefficient? Of course, if I look at that, I can do nothing. So this is a Stechkin idea, is that you take this one, and you take 2 points, sigma and tau. So you choose 2 points, and you take a parameter between 0 and 1. And what you do is that you look at this one, written so S minus lambda times Cy for tau. So I mean I take this one at S, this one at tau, and I take the first one minus lambda times the second one. Okay? So and now you look at what you get. Okay? So you will have something quite complicated. You will have that. I will take that this way. So what is the S? Oh. Something a little bit complicated. It's this one minus this one, but written as tau. Okay, so on the left hand side you have that, and then you have something here, which is that. That is the same as what I did in the previous proof. So I want to have a lower bound for this one, for the left hand side, and an upper bound for the right hand side. So I just want to have a lower bound for this one, and of course lambda is, so it's written here. These coefficients are non-negative, so this one is positive. So it means that this one is greater than this one. And the coefficients here are non-negative, so this one is a decreasing function. So it means that this one is positive. Okay, so you don't care about this one because this one is something which is positive. And I want to have a lower bound, so I will keep only that. It's the same as in the previous proof. In the previous proof I had only this term and I said that it was positive. But here again, the difference of the two is still positive, non-negative. Okay? On the other side, you have something which is complicated. So you have that for sigma, that for tau. But the key point is that you have something which is smaller than 1 here. Recall that I want to end up with something smaller than 1/2. So lambda is between 0 and 1, so this one is smaller than 1/2. Okay? And I have something complicated which is which I call term of S and tau. It depends on S and tau, it's this one minus lambda, this one at tau. But you don't care, believe me, this one will be negative. Okay, so what do I do now? I have a kind of a problem because in the previous proof it was very clear that all these numbers were non-negative. But here it's not that clear, so let me just show you what is the problem. So you want to deal with real zeros, so here you have many zeros. Let me just look at the real ones. Okay, sorry. Yeah. So in that case, if you look at this one, well, you don't need the real parts. It's 2 minus 4 minus Okay, and easy to see. So this one is positive because tau is greater than 1 and rho is between 0 and 1. This one is positive. This one is greater than 1. So this one is greater than is less than 1, sorry. So it's also positive. Okay, so it sounds nice because I want to have positive terms because I want to have a lower bound of the left hand side, okay? And I want to have a lower bound which depends on my real zeros. So for at least for the real zeros, all these terms are positive, okay? So it's very easy to get a lower bound, you just take the m plus 1 zeros. But the problem is that I don't do that, but if you look at that for rho non-real, this can be negative. And this is where Stechkin's lemma comes into play. So for the real ones, no problem. The Stechkin lemma is it's a very clever lemma. So you choose carefully lambda and tau, and you end up with something which will be always positive, and it's not exactly true. Is that what I do is that I will combine them for rho and rho minus 1. So the lemma is this one. So remember that I told you that you can group them in these pairs because they come in pairs, the zeros. And this one is always positive if you choose carefully lambda and tau. So lambda you must take 1 over current of 5, and tau depends on s, is 1 plus minus. So this is Stechkin's lemma. Okay, so I don't finish the proof, but now the end of the proof is the same as the end of the previous proof, because you can control everything here. What you do is that for the real zeros, you can forget about the non-real zeros because their contribution is non-negative, and you keep for the real zeros, any contribution is non-negative, so you just keep your m plus 1 0, and you do the same thing I did, and you end up with an inequality like here, but with a prime here. And here you have 1 minus lambda. And you do the same thing I did, and you have a contradiction for the choice, for the suitable choice of sigma. Okay? Okay, so this is what I wanted to say about real zeros of. Let me just add as a conclusion. The recent results which use Stechkin lemma. In their proof. Okay, so you can use if you can look at any proof that uses the Weierstrass product of this entire function of order 1, and you may hope that you can do something like that. So there are many proofs that you can where you can get a better result if you use Stechkin form. So what do we have? I will talk just about 2 recent results. So the first one is that it was known that the residue at s equal 1 of any zeta function is less than pt. So n is the degree. Okay, so this is a general upper bound on residues. Okay, and so I don't know which one is the name and which one is the first name. That's C. It was 12, I think. Using Stechkin lemma, he obtained something much better than that, which is much complicated to state. But the idea is that the constant here is much better. smaller than that, I mean. But the problem is that the proof is not completely explicit, and you have terms which depend on the degree, so and you have a constant in front. So the problem is that for fields of large degree, the bond is better, but it's not that clear up to which degree it's better than this one. I don't know. You have to work out all the details. Okay. The second result is that if you take a directed character, and assume that it's not quadratic. The problem is that to have a lower bound on the absolute value of the value at s equals 1. So it is well known that it dates back to Landau, that this one is greater than something. The conductor of the character. Okay, and what you want to have is explicit bounds. So if you look at the proof of that, it uses the infinite product and things like that. So it's clear that using Stechkin lemma, you should have something. So it was known that you can take at least for f chi large enough. Okay, so this was known. This is just an explicit form of this one. And if you use Stechkin lemma in the proof of this one, then you can lessen the bound here down to that.
What's inside the block? What's the symbol? S what? L?
L of 1 and chi.
No, inside the block.
The conductor S of chi. Okay, and maybe there are other reasons that you can improve using Stechkin lemma. I don't know if you have, if you use the infinite products, then likely you are able to improve. That's what you would get if you didn't use Stechkin lemma. Okay, so I have 5 minutes to talk about myself. Thanks a lot.
I think you're right on time now.
Yeah.
Yeah. So,
yeah.
Okay. Questions? No? Okay, yes. Question. So in my opinion, the Hadamard product is an explicit formula. Okay?
Yeah.
So you need positivity, you need primes, and you need zeros.
Yeah.
If you take another better explicit formula, and you try to optimize with respect to the test function, can you improve these results by using a different explicit formula?
I don't know. Because the Stechkin, you really need the exact, you need to have a sum over or something like that. You need something like that over zeros. It's only for these terms that you can apply Stechkin lemma.
For this time.
Yeah.
Because it's kind of like the rest of these.
Yeah, but if you don't have this kind of terms, you can do nothing.
More questions?